start. So both of these lectures act as pre-labs to the lab tomorrow. So we've got a lecture on Coleoptera and a lecture on Hymenoptera. So your handouts are down the front there for it. Relevant to understanding what we're doing and working with in the lab tomorrow. Okay, so let's start with Coleoptera, and we have the usual sort of outline here, which we're familiar with now because we've done the similar outline for both Hymenoptera and Lepidoptera. However, the one thing about beetles is they are the largest order of all animals in the world. They constitute 40% of all insects and 30% of all animals on Earth. Okay, so they're a huge, huge order. They give you a couple of little things here. So they are the big ones. So it's them, and Coleoptera has a massive amount of diversity. Ironically, it also has success in a number of other couple of things. There's an ad here I thought I'd play for you. Okay, so what that tells you, to remind you, oops, we're not going to go there, is that they are successful, just like the Volkswagen Beetle was the best-selling sort of car of all time, and indeed the rock group, the Beatles, is one of the most successful. So should all be able to remember that Coleoptera, extraordinarily successful group. Okay, so the largest order of living organisms, estimated 390,000 described species. That's huge. 4 suborders, 173 families, 500 subfamilies. So we go down to subfamily when we're doing King and Coleoptera because there is so much diversity that we've got to deal with. Australian fauna, 23,000 described species, 300,000, 265 genera, 121 families, 94 of those in Tasmania. However, in Australia, although we've got 23,000 described species, we're estimating we've probably got 80 to 100,000 species in Australia alone. However, only 3 of those families are endemic to Australia. If we added up all the fish, the birds, the mammals, the amphibians, the reptiles, etc., we'd have 8 times more described beetle species than we would all of those things. So it's an enormous group, and you should have no trouble in getting at least 5 Coleoptera families in your collection. What is the most diverse and speciose family of all animals in the world? It's weevils. We've got over 6,000 described species in Australia alone. Okay, let's have a look at these 2 pictures here to give us some perspective. This is the Titan beetle. This is about 17, 18 centimetres long, so pretty big, found in Brazil in the Amazon. So it's probably the largest insect that exists in terms of that, and heaviest, or largest, close to the largest and the heaviest, certainly in the top 3. However, we don't know what its larval stage is. It would be a wood borer. It probably takes out some sort of Amazonian forest trees, but we really don't know much about its biology. This one over here would be a mealful on its own right. It's a Hercules beetle larvae, which is one of those, actually like on my t-shirt there, like a Goliath beetle with a very long horn on it. And again, that is very large and very heavy in the top 3 largest insects in the world. So we've got the big as well in Coleoptera. Now the word Coleoptera comes from koleos, meaning sheath, and ptera, meaning wing, because it has that sheath over the wing. And the word beetle comes from Old English, which means little biter. And as you can appreciate, it wouldn't be a little bite that you'd get from a Titan beetle. It would damn well take blood off your fingers, that's for sure, if it got you. Haldane, who was a colleague of Charles Darwin and a supporter of Charles Darwin, commented, "The creator, if he exists, has a special preference for beetles. They basically occupy every non-marine habitat in the world and are enormously diverse in structure and obviously number." Okay, so let's have a look at where they fit in terms of relationships to others and their origin in the system. This is our development here, and we can see here that the first beetles were seen probably around 300 million years ago, or 295, yeah, 300 million years ago here. And we can see, like we have seen with nearly all other orders, a massive radiation when the angiosperms or the flowering plants came, but their numbers were pretty good here quite early on. And they're certainly much older than, say, the Lepidoptera, which we did last week, and the Hemiptera were older and did also exploit food resources. So we can see here that they're probably also exploiting the wood that all the gymnosperms and things were producing early on, all the conifers. So, and then moving on to other resources from there. In terms of numbers, remember we had 390,000 for beetles, we had about 160,000 described species for leps, so over twice leps, and 110, so it's over 3 times that for Hemiptera, so it is massive. If we want to look at the relationships of Coleoptera, we come down here, and they're related to what's called the Neuropteroid group, so that includes this group here, which is not found in Australia, which is the snake flies, this group here, the Megaloptera or alder flies, and the Neuroptera or lacewing. So they're most closely related to that. We can see one other order here that sits outside there, Strepsiptera or the twisted wings. Now they have an uncertain relationship, being possibly based on physical features closer to Coleoptera, but on molecular they seem to be more closer to Diptera. So they're sitting in an uncertain space as to where they are. But the Neuropteroid orders is that it's most close to. Higher level classification of beetles, like we have in all of these, and these classifications help us just sort out biologies, general rules around biology of beetles. We have 4 major suborders, and like all the other ones we've done with Lepidoptera and others, there's one suborder that absolutely dominates everything. So we have these 4 suborders, and this is the big suborder here, Polyphaga. And we'll go through each of these suborders in turn and look at some of the examples that there might be. So we'll start with Archistomata. There are 4 known families of Archistomata. 3 of those are in Australia. 50 species only worldwide, 10 species in Australia, and 1 or maybe 2 species in Tasmania. So it's not big, it's a small little suborder, very primitive, and what they look like is a very sort of soft-bodied beetle there, very small beetles. Their habitats is under bark and in rotting logs, so in that old Gondwana and sort of forest areas that you might, we have heard for some of these other small suborders in the other orders we've already dealt with. Myxophaga, again there are 4 families, but only 1 in Australia. Got a few more species, 100 species, but in Australia we only have 2. If you wanted to find something from this order, you'd be around river streams and river beds, and I'll show you the picture here of them. They're small, minute little beetles, little round things, not that much bigger than a grain of sand, so about 1 millimetre or so in size. You can see one here. They're aquatic, they live in river mud or sand areas, so these are sand grains, this one is in between. Possibly they're herbivores in that environment, and they have a number of fringes on parts of their body part and also on their wings. Unlikely, but it'd be fantastic if you did find one of those within your collections. Adiphaga, we're starting to get bigger. Not the biggest, but we're starting to get bigger. And I've listed here 1, 2, 3, 4, 5 families on this side and 4 on this side here. And these ones are aquatic, and these ones are mostly predatory ground-dwelling beetles. So nearly all the aquatic beetles are in the Adiphaga, and nearly all the Adiphaga are also mostly predatory beetles. So they're enormously beneficial beetles, and there's about 40,000 species across the Adiphaga. And I'm just going to give you a couple of examples of a couple of those families only. 2 in the water beetles and 1 in the predatory ground beetles. So we'll start with the family Gyrinidae. Here, also known as whirligig beetles. You may have seen them if you've been frequenting around sort of slow-moving areas in rivers. They're going to be floating on the surface of that river and moving around in little crazy whirligig sort of movements on the surface of the pond. They're predatory. They've got very much adapted forelegs for catching prey, and also all the things that we spoke about when we did locomotion and movement in insects, the flattened and fringed hairs on the legs, and modified. But they also, quite curiously, because they're right on that water surface, they need to look down and look up at the same time. They have 4 eyes. So here you can see them closely up. Here you can see an eye for looking up above the water surface and an eye for looking down below the water surface. So pretty cool setup for being a water surface dwelling predatory beetle. The other one that we also did touch on when we looked at insect respiration was we looked at the possibility of beetles diving down with bubbles or plastrons with them for carrying their oxygen needs. And the Dytiscids are one of those. They're a predatory diving beetle, and you can see it diving down here with a bubble. So in normal river environments or freshwater environments, these are important predators. However, if we want to go onto land, this family is probably our most important and significant one, the carabids or ground beetles. And as you can see from their forward-facing mouth parts, that we spoke about in the first lecture, they are predators, and you can see those mandibles out there at the front. So very fast moving predators, and as whole beneficial species for a number of different reasons, and I'll go through those with an illustration or two here. So here are a couple of the representatives of this family, Carabidae. Just see where I've got some notes here, but I don't think I have. And we can see quite a few interesting ones. These ones here, metallic looking ones with extra long legs, are often known as tiger beetles. Beautiful ones that you find more inland in mainland Australia. These ones are also more predatory ground, but here are a couple of interesting ones here. And these beetles not only take out other insects, but they also take out interesting things like slugs and snails. So this is a slug eater, snail eater over here. So and they also take out millipedes and things like slaters and things like that. So a nice diverse diet that you might expect moving around on the ground, and very beneficial in crops. So they're often trapped with little pitfall traps to try and work out the diversity of insects in a region and the health of that region through predators. Here's another bunch of carabids here that are slightly different in body shape, but again, you can see those forward-facing predatory mouth parts. We do have one species that's suspected to be involved with maybe damaging onion seedlings. It's known as the strawberry tiger beetle, but the proof of that still remains to be found. So it looks like it might snip off onion seedlings at certain times, but it's not yet really proven. But on every other one, we're thinking great to have them around. Okay, the polyphaga, as I said, we've got one suborder that's always huge, and in this case it's the polyphaga. It's huge. It's got greater than 90% of all beetle species, so you've probably got 29% of all animal diversity on Earth. 144 families with enormous variety and specialisation. So let's have a look at those for what sort of variety we've got, and I've just picked on a couple of families to illustrate it. First one, this one isn't of families, but it's just a fantastic hand-drawn illustration of a number of different beetles in the family Polyphaga, and you can see an enormous variety here in antenna, which is what this one is illustrating. But there are two families I would like to, three families that I would like to point out straight away in the Polyphaga for different reasons. So the first one of those is the Staphylinids, or rove beetles. These ones are going to be really easy for you to identify. Again, they're ground-dwelling predators as a whole. And you can see the easy identification is that their elytral wing cover actually doesn't cover their abdomen. It's only very short there, okay? And their wings are tucked up underneath this. So a very shortened elytra in Staphylinids, or rove beetles is their name. This one here is an interesting road beetle. It's known as the Devil's Coachman, with evil colours of orange and black, and you'll find that on carrion and forensic situations where it preys on fly maggots in those areas. But as a whole, again, this group is well used for biodiversity indicators because you can trap them easily in pitfalls, okay? And they're well described in those regions. Again, being predators higher order up and a good sign of whether environments are healthy or not. Scarabids are a huge family, close but not as big as the weevils, and I just wanted to point out a number of body shapes. We already looked at that scarabiform or C-shape body shape in larvae last week in the lab, but here we've got a number of different scarabiform, and I'll just point out there's a number of different foods that these ones are actually taking. So this is a cockchafer here, which is a root feeder, and then we've got another root feeder here and another root feeder here. So these will be taking out pasture areas in particular and can be problematic in control. Then we have a number of leaf feeders here, this one being the Christmas beetle on the mainland, and another one here, similarly called a Christmas beetle in some locations. But these are leaf feeders, for instance. Then we have some that are flower visitors, like these flower chafers over here. Then we've got some whose larvae are actually wood borers. So this is like this Hercules beetle. And then just to cap it off, we also have some that are, which we'll do in the last 10 minutes of the lecture, dung beetles, those that actually roll balls of dung or take dung. So enormous amount of food types, all found within that one family. So if we find a scarab, we've got to know a bit more about it than the fact that it's just a scarab. This one here, I really wanted to add, is weevils, and the most diverse family. But weevils have an elongated rostrum, as you can see here, not always so elongated in some, and in some it's ridiculous. So this is one known as the hose weevil, and you see the length of that thing there. You can try and speculate what the heck it's doing with a mouth part going right out there. But these ones here are known as giraffe weevils. So this is the male and the female, and the males fight each other by whacking their heads against each other for females. And they're found in Madagascar, I think it is, in the regions there. So enormous amount of diversity, but those mouth parts in these weevils is all situated in the bottom here, so they've still got the normal sort of chewing mouth parts, but they won't be taking great chunks out of things. They'll be taking small chunks out of things if they're weevils. Okay, now let's try and look at the characters that define a beetle. And they're all listed on your handout, so I haven't put them up in any way on this lecture slide, but I'll put up an image of beetles and talk about them as we go through them. So the first one on that handout is the prothorax, is well defined, represented dorsally by an undivided pronotum. So here we can see the pronotum, the first section, the first pair of legs, quite clear, quite easily, okay? We'll always see that. The second point there is the meso and metathorax is hidden pretty much underneath these elytra, but you can just see a small amount of it through a little triangle there in the back called the scutellum. Okay, so that's the only thing you see dorsally, the little scutellum. The forewings, the key thing of a beetle, are modified into an elytra, okay, which is a tough, rigid, sort of veinless cover over the abdomen, which at rest lines up perfectly along the midpoint of the abdomen there, as you can see. The fourth one there is the hindwings. Now the hindwings are underneath the elytra and they're membranous and they're folded underneath. It's in various ways, so they're hidden under the elytra and protected by the elytra. Those things, so the elytra is the big one. Then if we go to another aspect you'll be looking at in the laboratory is tarsal formula. Okay, what is that? That's the little bits on the feet. So we have a number of tarsi here, so this is the forelegs, so it's 1, 2, 3, 4, 5. Here again we've got 1, 2, 3, 4, 5. Here again 1, 2, 3, 4, 5. You can count them on this specimen, the same thing, that, not including the claw at the end. So that tarsal formula is 5, 5, 5, okay? Now we will get variations in that between 5, 4 and 3, and occasionally we will even get differences between the sexes where the legs are used in some way with mating, that males and females will have some slightly different tarsal formula. But these tarsal formulas are important in identifying your beetles down to family. The next one is the antenna. Antenna is usually 11 segmented or less. So here we see the scape, which we're not counting, and we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 11 segments along there. So it's 11 or less. However, there is one family, which is known as the longicorn beetles or cerambycids, that have very long antennae, and those are around 20 segments. So there is an exception to that general rule. The ocelli, those little tiny light-producing little bubbles or marble-like things that we've seen when we've been looking in the lab for insects over the last few weeks. With beetles, you'll never see 3 ocelli arranged in that arrangement, but you may see none, which is the case in this example here, 1 or 2 ocelli. And remember, those ocelli, when we spoke about vision, are involved with some sort of horizon detection and also with adjustments for light and dark levels for their main eyes, the compound eyes. So quite a number of roles. I'll probably mention more than that in that lecture. Okay, the 8th one. Okay, it's not unique to beetles, but it's part of why beetles are beetles, a little biter, really strong chewing mandibulate mouth parts. So we usually see a pretty good thumping pair of mandibles some way that move in a horizontal plane when they're adult, sometimes at the tip of the snout, like when they are weevils, for instance, but certainly they're there. And the last one, which we learnt last week when we were doing a tabulation in the lab, is that you have no abdominal cerci. Okay, so we did that last week when we were looking at the 5 orders underneath the microscope last week. So those characters are all important to beetle, but the big one is the elytra, and we'll return to the elytra and the importance of the elytra in terms of the domination of beetles currently in the world. Okay, let's now mess it all up and look at larvae. And as we know from the previous lectures, aside from the hemimetabolous Hemiptera, larval morphology can get more difficult than adult morphology. But we've got a number of different larval types that I would like to, larval features and some larval types that I would like to elaborate on. Okay, so larval diagnosis. Now we did this last week pretty much in the laboratory anyway when we were trying to identify. So the first thing is we've got a well-developed head capsule. If you remember, that doesn't have an adfrontal suture on it like it does with a Lepidoptera. It's just a straight, well-developed head capsule. So we'll see that in nearly all cases. Stomata, which are the visual organs of the eyes, 6 or fewer. Maybe that's not, a Lepidoptera would have the same thing. Mandibles are opposable for chewing or moving in a transverse plane. Yes, but so do Lepidoptera have that. Silk gland, always absent. Okay, this would be needing a dissection or a look in the mouth parts with a tiny little spinneret. But it is a nice, interesting characteristic thing. If you're seeing silk around, when you're looking at something, you know it couldn't be a Coleoptera, okay? It couldn't be a beetle larvae that's involved. 3 pairs of thoracic legs, yes, everybody has that. But abdominal prolegs are usually not there, but if present, they're never on segments 3 to 6 or 10. Okay, so there is a little bit of positional stuff that we can say about the prolegs, that they're rarely there, but if present, they're only never on certain segments. So that helps because remember we see prolegs in some of the Hymenoptera larvae, and we certainly see a lot of prolegs in Lepidoptera larvae. Functional spiracles, absent on the metathorax, okay, in the larval stage. So those things will help us, as we've already had a good look anyway in the laboratory in larval diagnosis. What we haven't sort of looked at is just then trying to look at different larval body forms and trying to make some guess, if you like, or derivation about what their biology may be. We've had a little bit of a look at some of these in 1 or 2 of the lectures, but here for beetles and in general we see them quite a lot. So we've got 7 different forms here, and I'll produce slides to follow of those different forms. But we've got Campotiform, which are long legs and active, Eruciform, which are caterpillar-like, Scarabiform, which is grub-like, C-shaped, Apotus, which is legless. We did mention Apotus in a previous lecture. Then we have some slightly nastier terms, Orthosomatic, which is elongated and parallel-sided, Anisiform, which is flattened, penny-like if you like. Oh no, sorry, the last one, Platyform, is flattened, and Anisiform is like little plates expanded over it, like you do see in slaters. So let's have a look at those, just to get familiar with those, and we'll look at those different body forms in the laboratory tomorrow as well. Okay, so here we have 4 of those forms. So this one here is the Campotiform, which, remember, if we said here, had long legs and active. So we're going to see, we can see the forward-facing mouth parts here. These are likely to be predatory, fast-moving predatory larval forms of beetles. So we'd expect those to be predators. We'll see those in things like some of the rove beetle larvae, for instance, is an example of one of those. Eruciform, well, it's got the 3 pairs of thurl legs, but that wouldn't be a fast-looking thing. It's like a big barrel or a keg on legs, isn't it? So it just sits there and feeds on leaves, if you know what I mean. So that would be a leaf beetle larvae, for instance. So downward-facing mouth parts, just feeding away. No surprise there, but we'll see quite a lot of Eruciform or caterpillar-like larval types, particularly if they're external foliage feeders. This one here, Scarabiform, we've already looked at that family which had such diversity in adult feeding, but a lot of the Scarabiform, all the larvae are this shape, and they're generally underground, feeding on roots or in wood, rotting wood and things like that. So they don't, moving around underground, but they've got a nice long body shape here to help with digestion of that sort of poor resource. We spoke about the xylem thing being a pretty poor resource to feed on. Here we have Apotus or legless, so you might expect to see that in ones that are tunnelling in, say, wood, for instance. There's not much need for legs in wood. But all weevils are legless as well, which is quite interesting. Weevil larvae don't have legs, okay? So an interesting thing there. Here we have the other 3 larval types, probably less relevant in terms of your likelihood of coming across them from day to day, but one is important, which is the orthosomatic or the flat-sided here. These are the wireworms, and these certainly cause a lot of damage in vegetable cropping. So as a larval stage, you'll see they're adults, Electeridae or clip beetles, which you might be familiar with. Here is the Anisiform, the ones with the plates over its back, looks a bit like a slater. This one is a firefly larvae, for instance, that one that signalled, we spoke about fireflies and vision the other week. And this one's more in aquatic environments, a flattened one, Platyform. So just have a look at those outside of wonderful diagrammatic illustrations. This is something from pulled off carrion for forensic sort of purposes. And we've got all 3 types here. We've got this domestic or hide beetle larvae being Eruciform. We've got Campotiform here being a predatory rove beetle larvae, which is preying on maggots in there. Same with this one. This is a Anisiform. This is a carrion beetle larvae, again preying on maggots. And then the scarabs are likely just to be sitting underneath the carrion as a nice moist environment. Here are a couple of others that you're likely to see. We've all still got head capsules, and I'll give you an example. I'll show you that one close up in a moment. But that's a Apotus, that's a weevil larvae, and a legless weevil larvae, but there could be other beetle species as well, but certainly weevil larvae are legless. And orthosomatic, that long, narrow wireworm shape. Here we go. This is looking at the head capsule here of the weevil, so we can still see all the things that you expect to see, even though it's quite sort of hidden, if you like, and recessed a little bit in there, in the mouth parts. Okay, let's have a look at general biology of beetles. And there's one thing I want to start with, which is the elytra and the importance of the elytra to beetles. So we've got a cutaway example of a beetle here. and the elytra or wing cover over that beetle. Now there are a number of advantages that the elytra or wing covers have achieved, which collectively probably lead to their significant importance. So firstly, it protects the flight wings. That's obvious, the flight wings are underneath there. Secondly, if you're imagine a dragonfly trying to hide in a little space with its wings out here like this, because you've got it all back, you can hide in much more cryptic and smaller spaces and still protect it, so it enables you to occupy enclosed spaces in cryptic habitats. It also enables you to provide some sort of crypsis or camouflage from your body for having that all being able to not just a clear wing, you can camouflage that wing so you look like something in your background. It fourthly provides protection from predation, so it's a nice hard cover that a predator might so easily get you, or indeed a microorganism might not so easily be able to get into the region that it needs to attack you. But probably the most interesting thing about it, and the purported most important one, is it encloses the spiracles. So if we can see here, we've got all the abdominal spiracles and the metathoracic spiracle. All these are enclosed. What does that achieve? That means that you can withstand very dry conditions. Remember when we spoke about spiracles before, and we said spiracles might be recessed in arid ones because you've got wind flow over them and stuff that would mean you'd lose a lot of water? Well, they're not losing a lot of water because it's all enclosed in this wonderful little space underneath there. So it really helps reducing water loss. And when you look at when beetle radiation really took off, which is in sort of the upper Permian and the Triassic, it was a very hot time. So they had an advantage there in not drying out through that. So it probably was a very significant step in beetles' dominance of life forms. In terms of general biology, I'm just going to throw a few slides here to point out the diversity of diets, and then go to a few pest species. So this is leaves, so these scarab Christmas beetles, and as we can see here, feeding on, in this case, eucalypt leaves. But as larvae we see a similar thing, so these are a leaf beetle larvae. This one is Paropsis tasmanica, which is a beautiful beetle, looks a bit like a ladybird but much larger. So we've got both larval stages and adult stages clearly being leaf feeders. This one here is that one that has the longer antenna, the cerambycids, the longicorns. You can see the antenna sweeping back over the back with a pair of jaws like that. It's very fitting that it's a wood feeder, so it can really, bite in and destroy parts of wood to get into where it needs to, quite clearly from that. This one as well, lecanids, which we see, we've got a Christmas beetle species that's a lecanid here. There's also another wood feeder in its larval stage. This one happens to be a male, so it has very enlarged mandibles for fighting with other males. Jewel beetles, the ones that we saw a few weeks ago, I think, that were frustrated trying to mate with beer bottles in the West Australian desert, they too have a larval stage that is wood boring. As an adult, they're interested in flowers and beer bottles. Okay, we've got predators as well. I've already mentioned that carabid, that ground beetle. This one is that subgroup in the ground beetles, the tiger beetles. It's just a lovely photo. I had to put it up. I really, really love tiger beetles in terms of them. And you can see those mouth parts out the front there. We also have many that are important, significant predators in their larval stage, and ladybirds is one of those. We can see here, this is a ladybird larvae feeding on aphids. And in this case here in forestry situations, plantations, this ladybird larvae is feeding on first instar and eggs of pest beetle species as well. So really, really important for control, and there are indeed ladybird species that are reared and released in a number of biocontrol places around the world. We also are involved with breakdown of products. These ones are all carrion beetles, so if something happens to die, these things will be one of the ones in there. You can see quite a nice diversity of them here. And the last one second last one I want to mention, but I will go back to these, is one of the classics of all time, the dung beetle. So here is the dung beetle rolling the ball. taking that along an area. So really industrious little ones, obviously very important, and we'll go to that in the last part of the lecture. We did speak about coppers and blues being down ants' nests. Well, we get some beetle families too that are down ants' nests, and there is a great video I'll show in between these two, which is on Milo, about how some of these beetles get into different nests and social insect nests. So again, they're doing the cryptic thing and having some sort of chemical that makes them think that they're actually like ants. Okay, let's have a look at a few examples of pest status for beetles. I wanted to highlight a few species here, and with your handout I've also given you a lot more detail on, I think, one, which is the red-headed cockchafer. Okay, so here's the Colorado potato beetle. This is probably, bad guy number one in terms of sort of American agriculture. It's moved up from South America and strips potato plants. We've got specimens of these, which, if I remember, we'll put them out for you to look at as well in the lab tomorrow. So certainly a major damaging plant. They've gone to BT potatoes, for instance, to try and get around it in North America. It's also got into Europe recently, so it's an interesting case. This is our Australian version of something that's got around the world. And this is Gonipterus, or the gum snout beetle. And you can see its larvae here. It doesn't have legs, but it's got a nice sort of fecal trail out the back of it. But this has got around the world to a lot of different areas. So the Gonipterus has moved to lots of South Africa, through here, through South America. It's now just found its way into California, and it's also through parts of Western Europe as well as New Zealand. So every year I have at least someone coming from the last few years. I've had people from Portugal coming down here looking for biocontrol agents for gum snout weevil, and we've just discovered a couple of new relationships that could be important for biocontrol of those around the world. But it's a big problem all around the world, so that's international pest species. This one here, freestanding wood and timber, is not immune. Doesn't have to be fresh timber, it can be cut timber. So we get a number of wood boring beetles like the furniture beetle. We spoke in the lecture on acoustics about the death watch beetle banging its head against the tunnels there with the sound of death coming. Stored products, weevil's fantastic for that. So there's weevils, nice little holes all through that bean there, with the bean seed weevil. So that's the sort of damage we're going to expect from a weevil. I'm not going to be able to take great big chunks in one thing, nice little things like that. Root feeding, this is probably the one that's most interesting to us, or one of the group, the cockchafers, but the red-headed cockchafer is one that's moved seemingly from northern Tasmania down to southern Tasmania in big numbers in the last 10 years. This is just a soil sample underneath, and you can see lots and lots of red-headed cockchafer underneath there. Accessing those is hard with chemicals, the old organochlorides and things that have a great residual effect, but other nasty side effects are no longer really available. So getting access to red-headed cockchafer can be hard, and really your handout says a lot more about red-headed cockchafer. But if they've come in there, your grass sort of lifts underneath it, and then things like the currawongs and crows and things, ravens, just come in and sort of push it over. So it can be a real mess if you get large amounts of red-headed cockchafer, and it is, as I said, elaborated more in your handout. This one is another weevil species that is an interesting pest species. It's come out of South America and got its way around the world. It's the white-fringed weevil. It's a hermaphrodite, so it's got both male and it only produces females. It's parthenogenic and only produces females, not hermaphrodite. And we have it here. It's a pest of root feeding crops in a number of different environments, but it doesn't travel very far. It's one of those that has to be almost taken by agricultural machinery because it's flightless, its wings are fused. But there is quite a bit of concern for that, feeding of our larvae at least into, say, potatoes as one of our major root crops. Just get to the beneficial related ones now for a few before we move to dung beetles. So here we have ladybirds as adults. This one is a Tasmanian species, Coleoptera. It's a big predator of psyllids, which you're now familiar with in the Hemiptera group. And we do have a pest species of psyllid, the tomato potato psyllid, that's coming. Now it's invaded from New Zealand into Western Australia, and there's a monitoring program which we used to run for about the last 6 or 7 years, looking for the psyllid to come into Tasmania and the east coast. And these are great psyllid predators, so they've been argued to be useful in knocking down tomato potato psyllid, but really the environment they live in is probably not that where potato plants are likely to be, so I'm a bit dubious about that. Biocontrol agents, we've got many beetles that are biocontrol agents and have been very successful. This one is one that was introduced into Tasmania in the 1930s, the gorse podweevil. So it's the first of many biocontrol agents introduced for gorse. You see with a lovely long rostrum like that, it's got in and starts chewing up all the seeds in the gorse pods. The other beneficial, which we'll go back to, is dung beetles. We'll talk about dung beetles more in general, but this one is its own family for you. So if you get one of these geotroopers, it's great. Otherwise known as the blue bombers, they start flying around now and are a winter active dung beetle in Tasmania, and I'll talk about those in a little while. This one I wanted to just put a little quirky bit at the end about possible products that beetles have. This one is a product called Spanish fly, or Cantharum. I went to the internet yesterday when I was preparing this lecture and found that actually, yes, you can buy it online still, a Spanish fly. But what is, it's a chemical extracted from ground up cantharid beetles, a particular beetle, and it causes an aggravation in the urogenital tract, which causes swelling. So it was a human aphrodisiac, if you like, of its day. It was the Viagra of its day in the 1700s. And still exists out there today. So it also, it's not necessarily the best thing or the dose that you might get. So the person, the gentleman that I've got there on the left, is Marquis de Sade, who only lived 60 years but was very famous for his hedonistic lifestyle. And one of the things amongst many, basically sadism comes from his name. He had very weird sexual habits, but some of the things he was found trial for was killing prostitutes through oversupplying Spanish fly in his relationships with them. He ended up in lunatic asylums for years. He wrote erotic literature. He was a really, really weird but interesting character in history. So Spanish fly, human aphrodisiacs. Probably head to Viagra more, I would recommend, maybe, than Spanish fly. Economic importance. I really only wanted to head to one of those. And I wanted to do dung beetles because I just really love dung beetles, and the Australian story is a great story. So there is a video there on dung beetles on your Milo, but I won't show that to you today. So you're welcome to look at that in the whole program. But dung beetles, loving dung, so how good could it be? Okay, so this is Australia before dung beetle introduction. We didn't have cattle, we didn't have sheep, we didn't have all those things. Kangaroo, for instance, lays a nice, solid little pellets. Not that attractive, but we did have our own species of dung beetle, okay, in these areas. But when we started with the first fleet and the introduction of cattle, we provided another resource that was out there, a big sloppy poo, if you like, that they produce. So our dung beetles are more interested in forested environments and these sort of more fibrous, small pelleted dung. So there was an opportunity. And this is the problem that we had, and I've done some maths on this here. So every cow produces 1 to 2 litres of dung per pad, and it lays about, it drops about 8 pads per day, which is about 20 kilo. We've got 28.5 million cattle, or 228 million dung pads being dropped around Australia per day, which is equivalent to about 170 million tonnes of dung per year. So it was perceived, started to talk about this in the 60s, as a major problem. And if you can't get an idea of what 170 million tonnes of dung is per year, we could try the MCG on grand final day. And here at the MCG you can see the goalposts, which are about 16 metres high. If you go up to about 26 metres high, that's sort of the amount of dung that has been spread and put all around Australia for many times. If you want to go to records for dung, then you can't beat this backside here. Elephants produce about 65 kilos of dung in a day, which is the equivalent of about a wheelie bin every day of dung. So we had an individual who was based in CSIRO at the time, George Bornemissa, who lived only a kilometre up here in his retirement, died a few years ago now, who thought, well, what could we do about getting rid of the dung that's lying around all over the paddocks? He said, well, we could introduce dung beetles. So his idea was that, so they went exploring. Here we are in South Africa looking at, I presume, an elephant dung there. Elephant dung, you can get up to about 7,000 dung beetles in one elephant dung. So a great place to find dung beetles, and even better that you get road signs that tell you you've got to keep out of the way of the dung beetles. So that was the option that they were looking at, and what they did, let's see where my slides are going, there's a number of political stories behind this, but in the 1960s in Canberra the politicians got a lot of bushfly, alright, and I'll speak, maybe I should go to bushfly in a minute and then we'll go back to the story. So here is cattle sitting out there, and you can see lots of dung around there, and the grass around that is basically made useless by dung. Not only that, but here we can see it also provides an area that what's known as a rank grass around the dung, which is not palatable on top of that. So you're losing large areas of your pasture by dung that is not being removed from the environment. The most annoying for your average urban person was this species, the bushfly, Musca vetticissima. Okay, the bushfly is the thing that if you go to mainland Australia at the right time of year, sort of May, sort of autumn, etc., then they're going to be hanging around on your back, in your face, in your eyes. They're waiting for you basically to defecate. Okay, they're a native species, but they breed in dung. Okay. This was a problem for the politicians in Canberra, because Canberra was one of the peak areas where it came through. So the politicians didn't like it, and then, lo and behold, they were going to have Queen Elizabeth visit as well in the late 60s. So they thought, oh, we've got to do something about this. They also looked at it from a tourism point of view. Well, it's, people want to go and look at the wildflowers in the spring, but when you're being covered with bush flies, it's a real problem. So from a tourism perspective and from a politician's perspective, it was something that they need to think about. So on January the 28th, is it, 1968? January the 30th, 1968, the first dung beetle was introduced to Australia into Townsville from Africa. Okay, and there were a number of points of origin for dung beetles from Africa and Europe, two of the major areas that they came in from. We've got some drawers in the laboratory that you can look at tomorrow around dung beetles. But the funding actually came through that period. The funding lasted from the late 60s right through to about the early 80s. Problem wasn't solved, but politically they just didn't care anymore. It wasn't entirely solved. This one here was a major problem in the north of Australia, which is the buffalo fly. It's got those rasping, nasty mouth parts that annoy cattle completely. It's coming from Timor, and they wanted to try and control that, and that also breeds in dung. So there was a amount of funding that was available through the meat industry to start the dung beetle program. These are the sort of dung beetles that you want to look at. We have three types of dung beetle. We have dung beetles that are tunnelers, that go down. Dung beetles that actually sort of, what have I used? I think I've used the words here on your handout. There's ways of saying it. Have I? No, I didn't. Oh, yeah. That are tunnelers, ones that nest, ones that actually are ball rollers. So you can see these here rolling a little ball. And these ones that actually nest inside the dung pad, and they're actually producing their young inside these, so that's what they're laying. These are the food resources for their young. These are the ones that we're interested in, burying the dung, okay? This is a dung, kilo of dung sitting out there in Africa, in Pretoria, and this is at 24 hours later. So you can imagine there are a number of really good benefits for burying dung, and one of those is bringing a lot more nutrients back into the soil. And here is an example of an experiment where we have dung with dung beetles, and this is the best type. No fertiliser, this is just sort of dung lying around but no dung beetles. So there is a significant difference there, not only that, but burying it through there. And I've listed a number of other important things that dung beetles have achieved. It's not only cleaning up pasture, it's on your handout, replacing nutrients, we've mentioned to already. But increases water penetration into the soil, so this is water with and without beetles. And that water penetration almost means you get better root penetration, soil aeration. We're destroying the breeding sites for the flies, and we're also reducing some gastrointestinal parasites, which also cycle through the dung. Tasmania, we've introduced 11 species, but only 4 have established. These 4 here, these 3 you're likely to have found over the summer. This one's starting to move now, it's more winter active. Recently there's been a 5th species introduced, but we're not too sure how well established that is. So this is the largest of those dung beetles. What was the wash up of all this? Well, this is a bushfly, annoying bushfly around your lips. They're varying sizes depending on how much competition they've had in their dung pad. The wash up was, and here is what it's like without them. This is camel ear in the desert here. From footage not that long ago when the dung beetle wasn't working that well. You can see it's pretty horrific there. And we move on here to the next page, alfresco dining. That's what we've been able to achieve by the dung beetle program. Until the dung beetle program went through and finished in the early 80s, we couldn't dine outside. OH&S didn't allow it because it was just covered with flies. You know, we couldn't do that sort of thing. Now we can. So it's been a really, really, really good and successful program. And with that, I better leave the lecture.